Okay, well, I'd like to welcome all of you to the Institute of Continuing Education and to Madingley Hall this afternoon, this evening, and probably welcome back to some of you if you've already been in other lectures here this afternoon. My name's Erica Bithell and I'm the Institute's academic director in physical sciences. I'm also a materials scientist and I'm particularly interested in the structure of materials, how atoms fit together to make interesting materials, how we can design better materials, how we can do more and better with the materials that we already have. I'm also an electron microscopist and an electron crystallographer, so I'm particularly interested in symmetry and in structure and how materials fit together at the atomic scale. And what I wanted to do for this about 50 minutes, and then we'll have a chance for asking some questions, is to talk to you a little bit about how we as materials scientists can understand symmetry in materials and can use it and find out some interesting things about the ways that materials work. So let's start by thinking about what we mean when we say something is symmetrical. Usually we start off by meaning that we've got some kind of a mirror in place. So here we are, here's a rather lovely crannog on Loch Tay, and it's a beautiful still day, rather like it is here, no wind, the loch's like glass, and we can see a mirror in the scene. We see exactly the same below as we see above, one mirror. And there are plenty of other places in nature where we see mirrors, very often with an accurate replication of one half to the other half. So butterflies are a good example. We expect our butterflies to look pretty much the same on the left as they do on the right. And we're used to this for bigger things too, although there tend to be small differences, and we're quite used to the fact that we're not exactly symmetrical. We don't just get mirrors though. There are plenty of very beautiful natural objects which show what we describe as rotation symmetry. And I've deliberately here put up some rather old images of snowflakes rather than new ones because this is still remains one of the most extensive collections of snowflake photography ever. It was put together by an American by the name of Wilson Alwyn Bentley in the late 19th, very early 20th century. And he developed a way of catching snowflakes on black velvet, and he then held this outdoors in the cold under a microscope and learnt to photograph onto glass plates through this microscope. And he did this so well and so beautifully, and this is only part of the collection, and these numbers go up to 900 and something. He did it so well and so beautifully that pretty much nobody bothered for about 100 years to try again. Of recent years, there are some more sharply focused images available, but these are a lovely collection all the same. So what do we see? We see things that have what we call hexagonal symmetry, but they don't just have a hexagon. They have a set of mirror planes, top to bottom, left to right, up and down. And in fact, they've got two sets of mirror planes because they're not just the same left-right, they're also the same top-bottom. So this is what we call point symmetry. All of this symmetry, all of these symmetry elements, in each case, pass through a single point. We like drawing things with point symmetry too. Here's a sketch of a piece of Celtic knotwork out of the Book of Kells. If we look at that carefully, we can see that this goes round just 3 times. Another piece of Celtic knotwork at the bottom is trying to play a trick on us. We might think that we've got a couple of mirror planes there. But no, if we look closely, because of the way the knotwork crosses, we've actually only got a twofold. There's no mirror because it's not replicated above and below. Sometimes we get other tricks played. When you first look at this one, most people think that's a threefold axis because they see the pieces in the middle. And then they think, hang on, something's not quite right here. And they look at the bottom and they think, maybe this is going to be a mirror. And then they look carefully at the top and we discover that this one has no identifiable symmetry at all. So if I wanted to label that as a crystallographer, I'd just label it 1, because I have to go all the way around completely to get back to where I started. So we quite like making repeating objects too. Here's a quilt from the Los Angeles County Museum of Art, and we can see in our repeating objects, we can see mirror planes again. We can imagine that you could have made this quilt bigger and bigger. And if we did that, we'd be able to put a mirror plane down the middle, and the left would look the same as the right. But we could move it over a bit, and we could find another mirror plane, and still the left would look the same as the right, because if the quilt was truly enormous, we wouldn't be able to see the edges. And that's pretty much what crystals do in materials. They're so huge, so many repeating objects, that we see inside each little element a little bit of symmetry. This quilter didn't get things quite right. She's made the odd mistake. If you look carefully, I think she was getting tired when she got to the left-hand edge. There's a little piece the wrong way up there. Something's not quite right there either. So it's not perfect. And we need to keep that idea of imperfections in symmetry in mind. We don't just get mirrors. We can go round and round as well. So if we forget about the edge of this quilt, here we have something which is clearly fourfold symmetry, but it's not, it is a square and yet it's not a square. There are no mirrors in this quilt. We have to go round once, twice, 3 times, 4 times to get back to where we started. So we've now got a fourfold rotation and a repeating, what I would describe as a periodic object. Objects that repeat over and over exactly the same actually aren't all that common in nature at the sort of length scale that we can see with the naked eye. Probably the best known example is honeycomb, and in fact I had to search for a long time to find a good image of a good piece of wild honeycomb that hadn't been supported on a ready-made wax grid. But still, we see the 6-fold symmetry there. We love making repeating patterns. This is the Alhambra in Granada in southern Spain, and it contains some very beautiful examples of tiled mosaics. And we see the same kind of repeating patterns and periodicity that we were seeing in the quilts. Repeating again because the tiles are all the same as each other. So here's a 4-fold pattern. Here's a 3-fold. This one is interesting because if you stand back and look at the colours, you can see that the 3-fold symmetry is no longer there. The 3-fold depends only on the shapes. The colours take away almost all of that symmetry. So I'm going to talk about something completely different now we've done our little introduction to symmetry. I want to tell you about an example where symmetry and losing symmetry is really important to the way materials work. And we're going to talk about jet engines. So here's a section through a jet engine. And for those of you that aren't maybe so familiar with them, let's explain a little bit about how they work. The air comes in at this end. It's forced through the compression section. The fuel is injected about halfway along. Combustion occurs, things start to get pretty hot, and because of the increase in pressure in that area, the exhaust then is pushed out through these turbine blades at the back. And the effect is that the jet then propels forwards. Now, the efficiency of this engine depends largely on how hot and how efficiently you can make combustion work. But the problem with that is that the hotter this section gets, the hotter the exhaust gases are, that have to pass through the turbine blades at the back. So those turbine blades have got a tough job to do. And it's those turbine blades that we're going to have a look at. This is what one looks like for real. This is actually the other way round from that section. So this at this end is where the combustion happens. This is part of a Rolls-Royce aero engine. And you can see the individual little turbine blades in 2 rings around those sections. This is how hard they have to work. That area is typically running at 3/4 of the melting temperature of the metals that those blades are made from. Most metals start to soften significantly at about 2/3 of their melting temperature. So there's something quite special going on there already. They're going round at 10,000 RPM, and the end of each tip is going round at about 1,200 kilometers an hour. That means that the end of each blade is travelling at a speed which is roughly twice the forward speed of the jet. They last about 3 years, and while they're in service, each individual blade, as it's operating this engine, is extracting almost enough power to power 1,000 of our homes, each blade. They get a bit tired after they've been doing that for 3 years. So here's one that's been taken out of a Rolls-Royce engine. This little piece on the left-hand end is where it fits into the central disc. You can see a row of little holes down this edge, and that's part of the mechanism for cooling the blades. There's cold air forced through as well as the hot air passing across the blades. And that helps to keep the temperature down a little bit. But we said we want to get these temperatures as high as possible. So what can we do to keep the temperatures up without having a failure? If we want to work out how to do that, we need to understand a little bit about how metals fail. And if we're going to do that, we need to understand what they look like on the inside. So let's start by looking at a piece of brass. Now, you wouldn't put brass in a turbine blade. They wouldn't last 5 minutes. But it has a very beautiful structure which helps us understand what's going on in other materials. So this is an optical micrograph of some polished annealed brass. The scale is that the whole width of this picture is about the size of a grain of sand. So each one of these little things, which actually I would call grains as a material scientist, each one of these little grains is maybe a 20th, a 30th of the diameter of a little grain of sand. Now, each one of these little pieces, where it appears all the same colour here, has its atoms all arranged in a perfect array, just like those quilts, just like the tiles in the Alhambra. Each of these is arranged perfectly. What happens where they meet? Here we go. This is roughly what happens where they meet. This is not atoms, this is a bubble raft. So this is little tiny soap bubbles, beautifully regular, floating on the surface of a tank. Lovely regular array at the bottom left, lovely regular array at the top right, something's not quite right down the middle. And this is pretty much what a grain boundary looks like. The atoms there aren't quite packed as well, they don't fit together quite as well, and when you put a load on a metal with boundaries in like this for a long period of time, they actually start to kind of slide along the boundaries a bit. So one of the things then that we can do to make things better in our turbine blades is we can decide that we're not going to have any boundaries. And that's exactly what's done for the highest efficiency blades. They're made by a process called investment casting, and you have a wax former, which is something like this little thing on the left. That sits inside a ceramic mould, and you very carefully let the metal in from the bottom, and it melts the wax away, and it forms inside that mould. And the way we get rid of all those boundaries is we start off with a little seed, like this little object here on the left, and then it's allowed to solidify slowly up this helical piece, which is called a pigtail. As it goes up the pigtail, whichever of those arrangements of the atoms is the most favourable wins over all the others. So by the time you get into here and into the blade, instead of little grains a fraction of the size of a grain of sand, we have just one grain. And these turbine blades are typically a few inches long. So here, inside this blade, every atom is arranged quilt-like, tile-like, in exactly the right place through the whole of that volume. So that's good. We've got rid of all our boundaries. Is that good enough? Not really, because something else happens. Let's go back to our bubble raft. So this time we've got a pretty much perfect array of bubbles pretending to be atoms in the metal. What happens now when we apply a load to it? So this thing is going to get pushed from top left. Okay, so it's being pushed from the left, and do you see how it's shunting along? There's a little gap in the middle, above the gap, to the right, and down here on the left. So rather than all of these bubble atoms getting messed up when you apply a load to it, it moves in particular places. So I was talking about bubbles on a bubble raft there, but atoms and metals aren't flat, they're three-dimensional things. So what happens when we stack up these beautifully hexagonally arranged atoms? Well, it's pretty much like stacking up oranges. If you imagine a stack of oranges, that's just what you get when you stack up a metal, atoms inside a metal. So here we go, a little picture at top left of what we get when we stack all these things up. And let's look at what happens inside a metal as we apply a stress to it and those atoms move across each other plane by plane. So let's imagine these are nickel atoms. Those turbine blades are mostly made of nickel. So let's say those are nickel. I'm going to put another layer on top, and for the time being I'm going to make that one a different colour so we can see which is which. Okay, and we're going to apply a load, and the top layer is going to bump its way over the bottom layer. And while it's doing this, you can imagine the metal changing shape, which is not good. So here it goes, it bumps from place to place. Let's check that again. Let's see where these atoms go. This time I've made them the same colour so that we know that they're all the same. So each atom in this layer is sitting exactly above 3 in the layer underneath it. Here it goes, bumps once, and every atom drops itself back into a place which is exactly like the place it's just come from. Let's do it again, and it's the same again. Every atom lands in a place which is exactly the same as where it came from. So now we can start playing games with the symmetry. I said the turbine blades were mostly made of nickel. Most of the time they are, but they're usually 3 nickels to 1 something else. The something else is very often aluminium, and a pinch of this and a pinch of that as well. But let's go with the nickel aluminium to start with. So what we've got here is the same thing. So this is like our layer of nickel atoms, but every third atom is aluminium. Now it actually comes out every 2 in every alternate row, but if you count up, you'll find you've got 3 blue ones to 1 orange one. So let's try that pattern instead. We'll put another layer on top. So now we've got the second layer again, 3 blue atoms, 3 nickels to 1 orange aluminium. And I've put it down very carefully and symmetrically so that my orange aluminium atom is sitting directly on top of 3 blue nickels, and it's also sitting symmetrically in between the 3 aluminiums in the row underneath. Let's bump it across and see what happens. So the atoms are all pretty much the same size, so they can bump site to site across each other as we apply a stress in exactly the same way they did before. Almost. Let's have another look at that. That orange atom started exactly symmetrically between the ones underneath. But its first bump puts it into a different place. Now it's sitting right next to another orange one. That doesn't look so good. It's not very happy. It doesn't like that. It has to go 2 steps to get back to where it started. And the same again. 1 step to a place that's not so good. 1 step to a place that works. So in order to make a metal with this kind of ordered structure deform, what we have to do is make the atoms work twice as hard. In order to deform it, it needs to go 2 steps at a time, not just 1. Here are four little things that all have something in common. All of them are objects which either convert a force, some pressure, to an electrical signal, or they take an electrical signal and they convert it to a force. So the easiest one to understand is the gas lighter. So this is the kind of thing you might use if you have a gas stove at home. You push the button and the flame comes out at the end. It's actually doing it via an electrical spark. So we apply a force and we get a spark, and it lights the gas at the end. The quartz watch is doing it the other way round. The quartz watch is taking an electrical signal and it's converting it rhythmically to the mechanical motion that makes the watch turn. The microphone, rather like the gas lighter in a sense, is taking a mechanical signal, it's taking the air pressure, and it's converting the pressure that's hitting the end of the microphone into an electrical signal that can then feed into our electronic system. The ultrasound machine has to do both, because it both has to make an ultrasonic pressure wave. So this is the kind of thing you might have seen, probably I'm sure all of the children, your mums and dads, saw you first on a machine like this. They're very commonly used when women are pregnant to check up on the health of the baby. So you were probably first seen on these. It has to do 2 things. It has to make the ultrasonic pulse, and it also has to record the reflection. So it has to convert an electrical signal to a pulse, and then it has to record the pulse that's coming back and feed it out through the electrical system. How does it do that? All of these things use something we call the piezoelectric effect. So they either take a force and turn it into an electrical charge, or they take an electrical charge and they turn it into a force. They get some mechanical motion out of it. How does that happen? Again, it's all down to the atoms and down to the symmetry. And if we're going to understand it, we need to start by thinking about an octahedron. Now, I've put this little thing in at the top because it's sometimes easier to see shapes on photographs because they have the shadows and everything. This is actually a little crystal of alum, aluminium sulfate. This one happens to be octahedral, and it might help you see the big diagram a bit better. So what have we got here? We've got an octahedron, which is 2 pyramids on top of each other. Lots of symmetry. The left is the same as the right. The top is the same as the bottom. The back is the same as the front. Whichever way around we look at this, we see mirrors in here. Why is this important? Well, it's important because there are many, many oxide materials which have arrangements of atoms which form into octahedra. So I've taken my octahedron here and I've put a little ball on each vertex, on each corner, and each of those balls represents an oxygen atom. Now, real materials don't have flat surfaces inside like this. They don't have struts between their atoms. So if you want to imagine what it's like inside a real oxide, you've got to imagine these balls being a lot bigger. So bigger that they touch, and so big that we don't have to worry about the flat surfaces in the octahedron. And then lots of these octahedra join together. This looks rather like our quilts again. This is the atomic structure of barium titanate, which is just one of a whole family of piezoelectric materials. We're looking straight down on the octahedra now. So the red atoms stand for our oxygen atoms, and we're looking straight down on the point of the octahedron. That's the top of the pyramid. The big green ones in the gaps in between are the barium atoms. Now we need to look for titanium. Titanium is sitting in the middle. Now, in the middle is hard to draw. I tried to draw in the middle, and I decided that it wasn't going to help you very much. So I decided that the best thing to do was actually take a slice through the middle of this octahedron. So here we go again. Now we've taken a slice through the middle, I can only see 4 of the oxygen atoms. And we find that the titanium is sitting right in the middle. They're sitting absolutely tucked in the middle of those oxygen atoms in the middle of the octahedron. So all of these atoms are really touching. Actually, they have a little bit of charge on them. The oxygens have a little bit of negative electrical charge on them. The titanium has actually quite a lot of positive charge, rather more than I've written there. At the moment, all of those charges are nicely balanced. Everything here is symmetrical. The positive titanium is right in the middle. The negative oxygens are exactly round the edge. But what happens if things move a little bit? Let's suppose something happens that makes all of those oxygens move in one direction a little bit, and the titanium moves a tiny bit the other way. So we end up with something like this. We've lost our symmetry. We've broken some of the symmetry of our octahedron. And the titanium is no longer quite in the middle. All of our positive charge has moved a little bit one way. All of our negative charge has moved a little bit the other way. And that's exactly what happens in barium titanate and other piezoelectrics. If you look at this picture of barium titanate, it's actually not quite straight. If you look at all of these octahedra, using a rather unscientific word, they're slightly wonky. Everything has rotated a little bit. And it's done that because all of the titaniums sitting in the middle of these octahedra are just slightly off-center. And that means that when we have a big macroscopic piece of this, something you could pick up, it has very slightly positive charge at one end, very slightly negative charge at the other end. Now, if you imagine squashing that octahedron, we're going to upset the symmetry even more. It's going to be broken even further. And it's going to change the distances between those positive and negative charges. And this is exactly what happens inside our gas lighter. So we have 2 bits of piezoelectric material, but they're face to face now. So they have their negative charges facing each other. And we come along and we squeeze it. That's what the clicky bit on the gas lighter does. So we apply force to it, it gets a bit smaller, and then it discharges across the gap. Makes our spark, and it lights the lighter. So all of our piezoelectric devices are working in some way like that. Each of these is either using the force that we apply, like the gas lighter, to create an electrical signal. The microphone is doing a similar kind of thing, but it's taking sound waves rather than the push of a finger. The ultrasound machines, we said, is doing both. The quartz watch is actually working the other way round. Okay, so that's an example then of something where we break symmetry, we lose some symmetry, and something interesting happens in a material, something interesting and useful. All of the things I've talked about so far have essentially regular, what we call periodic repeating patterns of their atoms. Let's have a think about these periodic repeating patterns. Here's a kind of quilt. I've made it rather regular this time. We could imagine this going on forever and ever. We could carry on adding tiles and we'd get exactly the same result. Actually, we don't just need to do it with squares. We can squash it and stretch it, and we can see that if we have tiles which just have a twofold rotation, we have to go around halfway and back again, we can still carry on repeating them forever and ever, and it's all fine. We can do that with things which have sixfold symmetry and things which have threefold symmetry. And we can carry on repeating these forever and ever. But we can't do that by going round 5 times. There is no way in which we can make a periodic object, something which keeps repeating the same pattern over and over and over, with pentagons, with anything where we have 5-fold rotation symmetry. Hold that thought about 5s for a moment. When I started, I said that there aren't very many things in nature at the level we can see with our eyes that make regularly repeating patterns like the honeycomb. There are quite a lot of things that do seem to have some kind of a pattern that repeats, but not quite like that. Take these sunflowers, for example. There's clearly a pattern to the seeds in the seed head, and we can clearly make seed heads of all kinds of different sizes by adding seeds on at the edge, but they don't repeat in the way that the quilt did. So nature here has a way of creating an object which can occur at different scales, but it doesn't do it by repeating exactly. This is what we call a Fibonacci spiral. And in fact, if you look at it, you can see there are 2 sets of spirals. There's one going clockwise, and there's one going anti-clockwise, kind of like curved spokes of a wheel. And if you count up the number going clockwise at a distance from the centre and the number going anti-clockwise, and do a little bit of maths, that'll tell you about how many spirals are needed to fill the next bit out. And you can do a little bit of maths again. It'll tell you about how many fill the next step out again. So this is a natural way of extending an object, but it's not periodic. It's determined, but it's not a periodic thing. This is a beautiful one. This is Romanesco broccoli. This does the same kind of thing. You can see that you can make it bigger and bigger and bigger. And the fantastic thing about the Romanesco broccoli is that as you look in at finer and finer and finer scales, you keep seeing things that look like little broccoli clumps. So you have a big broccoli head, and you look at a little piece of it, and it looks like a piece of broccoli, and you look in a bit further, and it looks exactly the same again, but on a finer scale. This is a different kind of spiral, because you can see that this time it's accommodating things that get bigger as it goes out, but it's also self-similar. Okay, so we've noticed that in crystals we commonly have repeating patterns, exactly the same everywhere. In nature, at an optical scale that we can see, we often have determined patterns that will keep going, but they're not periodic. And our crystals that repeat exactly the same everywhere never have any pentagons in them. So when this gentleman, Daniel Schekman, did an experiment in his laboratory in Haifa in the early 1980s, he got a bit of a surprise. Now, I haven't said anything about how we know how the atoms are arranged inside crystals. And very quickly, broadly what we do is we shine a beam of X-rays or electrons at them, and we look at the symmetry and the spacings of the spot pattern, what we call a diffraction pattern, that comes out the other side. The result, what we see, the way it changes the X-ray or electron beam. So he had a crystal of an alloy of aluminium and manganese, and he fired an electron beam at it. And usually when you do this for a metal, you expect to get fourfold patterns or sixfold patterns or threefold patterns. And he had a look at this pattern and he counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That doesn't look quite right. It's even worse out here, 1, 2, 3, 4, 5. And the spacings between these spots are actually pretty much the same wherever you go. He didn't tell anybody for 2 days because he thought he'd made a mistake. What he eventually decided was that it was not a mistake and that these patterns told him something about the internal structure of the material. This made him not a very popular person in his laboratory for a while, until people realized that the mathematicians had already worked out how to do it. This pattern up here is an arrangement of tiles which we now call a Penrose tiling. Now, it's coloured because it makes it easier to see the fives. It's actually made up of 2 different sorts of tiles. There's a rather fat rhombus, and there's a little thin one. They've got the black lines around the edges. The orange colours help us to see the pattern. So if we look down here, for example, we can see that we've got a 5-fold pattern. We've got 1, 2, 3, 4, 5 orange points. And around it, we've got a slightly bigger star, 1, 2, 3, 4, 5 again. And in fact, from this point, we can go out quite a long way, and we can still see 1, 2, 3, 4, 5-fold symmetry. We can go other places in here. We can still see 5s. There's a 5 here. It's a little pentagon, and another 5 round it. And again, we can go a bit further out. But this is not a periodic object. It has some rather strange properties. It contains 5-fold rotation axes, but there is no part of this pattern which is exactly the same as any other part. And by that I mean exactly the same to a great distance. So if I picked up this pattern and moved it across, if I just take a little piece of it, I'll find another little piece which is exactly the same somewhere else. But if I take a bigger piece and a bigger piece and a bigger piece, eventually I'll get a piece so big that I can't find another bit exactly the same anywhere. The other thing which is rather strange is that if you let these patterns get very, very big, so you keep adding tiles at the edge, like the quilts, like the crystals, on and on, somewhere you'll be able to find a piece as big as you like, which has perfect 5-fold symmetry. But you'll never find another piece exactly like it anywhere else. So this is called a quasi-periodic object. And what Daniel Schekman and the people he was working with realized is that actually this kind of quasi-periodicity was a new kind of crystal structure. It was a crystal structure which was ordered, but was never exactly the same anywhere else inside the crystal. The little object down at your bottom right there was one of the crystals that's been made much more recently. It's actually, this is a tiny little thing. It's about 5 millimeters across. But you can see that eventually, when they learnt to make nice single crystals, you could get beautiful facets on these, just like you get beautiful facets on minerals. Actually, we've been arranging patterns with 5-fold symmetry for a long time. going back to the tile patterns again, there are many places in the Middle East where you see very beautiful fivefold arrangements. They're often quite restricted. So they're fivefold symmetry, but they don't go very far. In recent years, as people have become interested in the Penrose tilings and have looked more closely, they've realised that there are a few examples which do terminate because they happen to reach the edge of the area that was being tiled, but actually the person who tiled them had understood how to put down a pattern that could keep going and going on. And this is one of a rather small number of examples, about 3 or 4, where we understand now how the pattern can be extended geometrically to much bigger areas. Okay, so Daniel Schekman had made these crystals. They were a bit of a laboratory curiosity for a little while, but they turn out to have some rather curious properties. When we looked at the turbine blades, one of the things that we said made metals weak was when it's possible for a plane of atoms to move across a plane that's like it underneath and land in exactly the same set of positions as it goes. Can't do that in a quasicrystal, because as soon as you try to push one set of atoms over another, they're all sitting in a place which is different from where they came from. So, rather like the turbine blades, we have a metal here which is very strong and very hard, because it's very hard to make these patterns of deformation move through the metal. As it turns out, they have some other properties too, which are quite interesting. They have very low adhesion. Organic things, don't stick to them very well. They're very low friction, very slidey. They don't conduct heat well, and they don't conduct electrical currents well, and they absorb infrared quite respectably well. And all of those things are very strange things for metals to do. It's not at all normal. So, can we do anything interesting with these materials as materials scientists? Well, we can't do quite as much as we would like to, because they turn out to be rather difficult and rather expensive to make in any large quantity. The strength and the hardness actually are being exploited. Sandvik in Sweden have a high-strength steel which uses small quasicrystalline precipitates, because they're very strong and very hard, embedded in the steel to give it some extra strength. I think the nicest example, though, is the one that I read in Daniel Schekman's own words. He said, the very first application was non-stick coating on frying pans and cooking utensils. But if you cook on quasicrystals, your omelette will not stick to it, like Teflon. Unlike Teflon, if you use a knife in the quasicrystal skillet, you will ruin the knife. When you have Teflon and you use a knife, hey, you ruin the Teflon. So I'm going to end up with my title. I still think it's simpler with symmetry, but it's a lot more interesting without.